All right, so we've got a differential equation, we've got an initial condition, and we just need to bring our dx over to this side and then integrate. So we've got dy that we're going to integrate, and we've got 3x squared minus 2x over root 1 minus x to the fourth dx that we're going to integrate also. So the left-hand side just gives us a y, and it gives us that constant, right? But we're going to just put one constant on one side since we could gather them all to one side. And then what is the integral of 3x squared?
X cubed.
Mm-hmm. And then this one's a little bit more difficult. So for this one, we hopefully see a nice little substitution we can use here. So we're going to rewrite this as its own integral for now. And hopefully we see that if u was equal to x to the, fourth, u is equal to x to the second, du would be 2x dx. And if du was 2x dx, I'd get rid of everything up there except du now. And down here we'd have root 1 minus u squared, right? Because x to the fourth is x squared squared. And then this should be an integral off of your integral rule sheet, right? What does that integral become?
Inverse sine.
Inverse sine.
Mm-hmm. So we got x cubed minus inverse sine x plus c. Sorry, not inverse sine x, inverse sine u plus c. Everybody good there? And then we'll replace the u with x squared. So we got y equals x cubed minus inverse sine x squared plus c. And now we'll be ready to take that and plug in our values and evaluate. Yeah. So it probably looks like we need a new page for that. Y was 1 over the fourth root of 8. And so that should equal, our x value is the 1 over the fourth root of 2. So we're going to cube that. So 1 over the fourth root of 2 cubed. And then minus our inverse sine of this squared plus our constant. Everybody good there?
Yeah.
All right. If we cube the 1, that's still 1. If we cube the fourth root of 2, we can just cube the 2, which makes that the fourth root of 8. And here, what do we have at the moment? We have the fourth root of 2 in the denominator, right? So this is 1 squared, and then we have 2 to the 1/4 in the denominator. And we need to square both of those. And so squaring this exponent, right, if we have something to a power to another power, we can multiply those powers together. True?
Yep.
Okay. So that's going to give us 2 to the 1/2, or just the square root of 2. 1 over root 2 plus our constant. It's just sort of a side note here. Right? And then what is 1 over root 2's inverse sine? We should be able to come up with that because we should be able to rationalize this, right? And see what this is equal to on the unit circle that we've always seen. What do I get if I rationalize that?
Root 2 over 2.
Root 2 over 2. And the 1/4, or the fourth root of 8 over, or the 1 over the fourth root of 8 and the 1 over the fourth root of 8 should cancel.
Yeah.
And so that should give us a constant of what? What's the inverse sine of root 2 over 2?
Pi over 4.
Pi over 4. Exactly. And so we then end up with our final function is y equals, what was it? It was 1 over the, no, it was x cubed. I don't know why I'm doing it. We just had a weird value there. It was x cubed minus inverse sine of x squared plus pi over 4. Everybody good with getting that function? And then we got to find the interval in which it's valid. If it's got some, it might have some discontinuities, right?
Yep.
All right. So what values can we plug into inverse sine? There's only a certain number of values. What? Say that again?
From -1 to 1.
Right. Which tells us that x squared has got to be less than or equal to 1, greater than or equal to -1. Well, x squared is always greater than or equal to -1, right? This part of it is sort of insignificant because this is always true, right? So really, we're just looking when is x squared less than or equal to 1, which would tell us that x needs to be less than or equal to 1, or x needs to be greater than or equal to -1. But there are no discontinuities within there. We just have a restriction on the domain. So we would note that this is just -1 to 1 inclusive, and that does include our value of the 4th root of 2, or 1 over the 4th root of 2, sorry. Good or no?
Good.
Any questions on that or no? Or anything else for that matter?
Nope.
Riley, I saw you sent me a question about the U substitution on this one. Is that did that do it? Is this the last question on the homework? Somebody else asked for number 8, but then I saw you. Yeah, okay, you're good. All right. Everybody's good on that one? Everybody good on that homework? All right, you got plenty more days to ask questions on it if you need to as we move forward into the quiz on that stuff next week. So cool. All right, let's take a look then at a little bit of a motion problem with our differential equation. So I'm going to give you a differential equation, ds dt, so that's the derivative of the position function because we often use s as position. So ds dt, or v of t, is t squared minus 8 over t plus 1 squared. And this is giving us the velocity of a particle that moves along the x-axis, and we're saying from t equals 0 to t equals 5. Now, we didn't talk about this 2 units ago, probably. We talked about it like 3 months ago, maybe a little bit, but the displacement of an object is always going to be the area underneath the velocity curve. So the integral of velocity tells you how far a particle displaces in the time period between your two intervals. So if I were to integrate something that was a velocity equation from 1 to 2, that would tell me how far the particle moved from t equals 1 to t equals 2. It doesn't tell me anything about its actual position. It just tells me how far it moved from t equals 1 to t equals 2. Does that make sense? Right, because the position is at t equals 2 is relative to where it was at t equals 1, which is relative to where it was when it started at t equals 0. So an integral of a velocity function gives you a displacement, the total, the distance it is from where it started, not an actual distance traveled, because that could be different, right? And also not a position itself.
right? How could the displacement and the total distance traveled be different if we're talking about a particle moving in a line?
Can you ask the question again?
How could the displacement and the distance traveled be different for a particle if it's just moving in a line, right? If I start here and I end here and I'm moving in a line, along a line, how could the displacement from here to here be different than the total distance traveled?
If it didn't move in a straight line between the 2 points.
No, but it does move in a straight line. It moves along this line, right? From somewhere from over here all the way
Could
along.
move like back
Turns
and
at any
forth.
point.
Right. Could move back and forth, right? I could do something like this. Right. And then my displacement is this, but my total distance traveled is all of these back and forths that I might do. Right. So it's important that we recognize the difference between those things and that it could be different. So what we want to be able to do is use the idea of a differential equation or use this idea of displacement to help us figure out where a particle might be at any given time. So what we want to do is figure out the particle's position at t = 1 second. And from there, we're going to also try to go from t = 5 and see how far it actually traveled. And we're given an initial position. So this initial position is like our initial condition for our differential equations. So if we integrate our velocity function, we should, from 0 to 1, know how far away it is from where it started at t = 1. So what's this interval going to become?
0 to 1.
What? What is the interval of this?
1/3 t cubed.
Okay. What about the second part? How do I integrate 8 over t + 1 squared? 8 over t + 1 squared is like 8 over u squared with u equal to t + 1. And du is still just dt. So it's really just 8 over u squared, or 8u to the -2. What's the integral of 8u to the -2? Go up to -1, divide by -1, which makes it a minus 8 over u. And since we already had a -8, it should be plus 8 over u. Good or no?
Yeah, good.
All right. So one way we can do this is evaluate this definite integral from 0 to 1 and say, well, what does this give us? It gives us 1/3 plus 8/2 minus 0 plus 8. And what does that give us? Should be 1/3 minus 4. What's 1/3 minus 4?
-11/3.
-11/3. So it's moved -11/3 units to the left. Well, if its initial position was 9, then where is it now? Should be at
9 minus 11 thirds, which would be 16 thirds. Now, there's another way we could have done this. And the other way that we could have done this is we could have integrated this and said, instead of doing it as a definite integral, we could have said, all right, the integral of t squared minus 8 over t plus 1 squared dt is equal to t cubed over 3 plus 8 over t plus 1 plus some constant. And we could have solved for the constant. This would be a position function, s equals t cubed over 3 plus 8 over t plus 1 plus c, and plugged in our 0 for t, 0 plus 8 plus c equals 9, and gotten a constant of 1. And so then we would have this function that told us the position was t cubed over 3 plus 8 over t plus 1 plus 1. And if we plug 1 into that, we get a third plus 4 plus 1, a third plus 5. And what's a third plus 5? It's the same value, 16 thirds. So we can treat this as the integral from 0 to 1, the definite integral as displacement, or we can treat it as an indefinite integral and find the actual function that tells us the position. Good or no?
Yeah, good.
All right, so where is this particle at t equals 5? We should be able to use this position function that we got. So having the function itself is very convenient because then I can evaluate at any value that I wish. So s of 5 should be what? Plug in 5, that's 125 thirds plus 8 sixths plus 1, which is what?
44.
132 thirds or 44. Now, last little thing down here. How far did the particle travel in the first 5 seconds? That's a little bit more difficult of a question, at first at least. Why is this difficult?
Because it's distance and not displacement.
Right, it's no longer a displacement, it's a distance traveled. The displacement's easy. We know it went from 9 to 44. That's 44 minus 9. We can figure that out. That's 35. That's easy, right? But the actual distance that it traveled could be very different. And so what we can do, and I'm going to give us a new page for this real quick here. The speed of a function is always equal to the absolute value of the velocity function. That's something that I briefly mentioned way back when we were first talking about derivatives. The speed is the absolute value of velocity. Well, if you integrate the speed function, this gives you a total distance traveled because it negates all of these negative values that we would get from the velocity and just makes them all positive. So the integral of a speed function is your total distance traveled. And so if we're interested in the total distance traveled in the first 5 seconds of a function that has this as its velocity, all we have to do is take the absolute value of that and integrate it. So we should get the integral from 0 to 5 of the absolute value of, what was it, t squared minus 8 over t plus 1 squared dt. And your calculator will evaluate that for you. So that's what you guys are going to do real quick, is have your calculator evaluate what that is.
we'll get a decimal approximation to 3 decimal points and see what we got. And if you're looking for how to do absolute value, it's in that math window also. I think it's like math, and it might be like option. I don't even know what option is, but you'll see it in there. If you click math, it's in there.
Why don't we include the +1?
Well, because remember, what we just said is that the integral of speed is the total distance traveled. So that speed is absolute value of velocity. So we're back at this velocity function again.
Oh, I see. Okay.
Yeah.
I got 42.59.
Yeah, I got that as well.
You got a third decimal on there? Was it a 0?
Oh, it was 8.7.
Always go to 3 decimals or more. 42.587. There were no units, I don't think, given in any of this, was there? So 42.587 units, we'll call it. Okay. Everybody good with that or no?
My video just dropped for like a minute before, so can you just explain briefly what you did on the other page with the t equals 5 seconds? What was going on there with that?
Yeah, so did you get the part where we found the actual function by finding the constant?
Yeah, and then it dropped, yeah.
Yeah. So we integrated an indefinite integral to find the c value using our initial condition, like we did yesterday with our differential equations. That gave us the position function was t cubed over 3 plus 8 over t plus 1 plus 1. And then all we did was we said, well, if this is the position function, to find the position at 5, all we have to do is evaluate this at 5.
Okay, and then how did that lead to the speed equals the absolute value of the velocity? Like what happened there to get to there?
Oh, well, it had nothing to do with that. The speed equaling the absolute value of the velocity is just, so if you think about a velocity function, right? And there's my velocity function. It's got some positive velocity. It's got some negative velocity. And when I take the absolute value of that function, I still have that first little piece, but then I got this and then this also. And so that puts all of these displacements, we call them, right, as positive values. And so it's just summing together each of these displacements. I went to the right this far. I went to the left, right, because I'm below. I went to the left this far, and I went to the right this far. And so that ends up being adding up a bunch of positives together to give you the total distance traveled. Does that make sense?
Yeah, okay, thanks.
Yep, no problem. All right, any other questions on any of that? Because the velocity question, that's, there's 9 different types of free response questions that you might see on the AP test. And one of them is some velocity, speed, motion type problems. And we'll practice those much more. In fact, we'll do another one right now. I'd like to give you guys 2 or 3 minutes to look at this one and see if you can, see if you guys can come up with how to solve this. So we're given a car that has an initial velocity of 5 miles an hour, and we're given its acceleration function. We want to know how fast it's going after 8 seconds, and we want to know how far it traveled during those 8 seconds. So I'll give you, I don't know, 2 or 3 minutes to try and sort through that and see if you can figure it out. Sound good? Okay, ready, go. All right, so we're starting with an acceleration function, and we're given an initial velocity. And if we want to find how fast it's going, we should just need to find a velocity function, right? So let's integrate the velocity, integrate the acceleration. What's the integral of 2.4 t?
1.2 t squared.
plus some constant, right? And
Yeah.
we need to figure out what that constant is by looking at our initial velocity. So we know that velocity equals 5 if t equals 0, which gives us a constant of 5, which tells us that the velocity function should be 1.2 t squared plus 5. Good or no? And what's the velocity?
81.8 miles per hour.
Should be what? Sorry.
81.8.
81.8 miles per hour. Yeah. Okay. That sounds good to me. Yeah. Everybody good with that? Okay. Now then the next question, how far did the car travel during those 8 seconds? So this time we got to think a little bit more here. So we got our velocity function. V of t is in miles per hour, right? 1.2 t squared plus 5 miles per hour. If we want to find how far it traveled, we should integrate the absolute value of this. But if we think about this, what's 1.2 t squared? It's always positive. And if we add a 5 to it, that's still always positive. So this function is never negative. It's always going to have a positive velocity. And if you always are moving in a positive velocity direction, shouldn't your displacement be equal to your total distance traveled?
Yeah.
Yeah. So if we integrate this, what should we get? What is our, how should we integrate this? From where to where?
0 to 8.
Okay, from 0 to 8. So we want to integrate from 0 to 8 our position function to find out how far it traveled. So what does that give us? What's our integral?
0.4 t cubed plus 5t.
Okay, now we've got a little bit of an issue here. And what's the issue that we've got? We got to evaluate this from 0 to 8, right? But 8 is in terms of seconds.
Yeah.
Yeah, and this is 2.4 t miles per hour per second was our acceleration, but when we integrated that, it gave us miles per hour. And so now our units for time are hours. And so this is 8 seconds. We can't plug 8 seconds into here. I mean, that would tell us if we plug 8 into this, that's going to give us 8 cubed times 0.4 plus 5t, right? I mean, that's going to be an astronomical number of miles that we've traveled, isn't it?
Yeah.
So 8 seconds, how many hours is 8 seconds?
.002.
Is that exact 0.002?
Two
So repeating 2.
Repeating 2? Okay. What is that fraction, 0.002 repeating? You had to turn, if you hit math on your thing, it should convert decimal to fraction.
1/450.
Perfect. So we're going to have to plug in 1/450 into this and figure out how many miles we went. And so what does that give us? It gives us 0.4 times 1 over 450 cubed plus 5 over 450 minus 0 plus 0. And you can give me a decimal for that, that's fine. Point something number of miles, right? All right, 0.011 miles. Sounds good to me. Which seems reasonable, right? Accelerating pretty quickly. 8 seconds to get to 81 miles an hour. Haven't gone that far though, because we weren't going that far, or weren't going that fast at the beginning, right? And our velocity really, our acceleration ramps up with each second, but we're not really increasing that much in the first few seconds. So.
Could you just plug that definite integral into your calculator? Would that have been like a way to solve this? Okay.
Yeah, if you changed it to 1 over 450 to begin with, sure. I should write this as hours. Cool. Everybody good there? Any questions there?
I'm just wondering why we didn't have to change the 8 seconds to hours when we were doing the first part of the question.
Yeah, good question. So the reason we don't have to worry about that there is because the acceleration was in 2.42 miles per hour per second. And so the base of that is it's miles per hour per second. And so when we first integrate that, that gets rid of the seconds, and we can do it in terms of seconds.
Okay, I see. Thank you.
And then it just becomes miles per hour afterwards. And so then we have to do it all in terms of a unit of hours. That makes sense, yeah?
Yeah, thank you.
No problem. All right. Let's see if we can do something a little different now. See if we can find the solution to this differential equation, f prime of x, or dy dx, if you prefer to write it that way, equals e to the negative x squared. Then we want f of 7 to equal 3. So here comes the difficult part of this. How do we integrate e to the negative x squared?
U substitution.
That seems like a great idea, right? U equals negative x squared and du is negative 2x dx. But where's my negative 2x? Negative 2 is fine to put in, but the x is not a constant, so I can't just throw that in. That's a problem. In fact, this is a bigger problem than you might expect. E to the negative x squared is a function that does not have an explicitly defined integral. You cannot just write a function that is the integral of e to the negative x squared. It doesn't exist. There's no function that we can just write out that has a derivative, and when you take a derivative, gives you e to the negative x squared. So there is no integral of e to the negative x squared. Yet
So
using what? Go ahead.
I was just going to say, why then don't we just say like no solution or something?
Because there is. Because there is a way to write out a function. And in fact, there's a way, let's say we wanted to know what f of 2 equaled. There's a way to find f of 2. We can find a function that is the integral of this function, for which f of 7 equals 3. And we should be able to use that function to evaluate f of any value we want. And generally, we'll use a calculator to evaluate it. But we could do the approximation of it by hand using any of our rectangular, approximation, trapezoidal approximations, all that stuff. So we have to think back a little bit to the fundamental theorem of calculus, which said that the derivative and the integral, right, are the same thing effectively. And so couldn't I then say that y is just equal to the integral of this function? And I'm going to write it in terms of t like we used to do with the fundamental theorem of calculus a long, long time ago. What's the derivative of this? What's dy dx or dy dt in this case if I took the derivative? It would just be this function, wouldn't it?
Yeah.
Yeah. But when we integrate, we have to add a constant in, right? But also, if I evaluate this at 7, I don't know how I'm going to get 3 here. And when I take the derivative of the integral of something, didn't I have to have limits on it to make it just come back to be the original function? What did the upper limit have to be? Had to be the variable we wanted it to be in terms of, right? What did the lower limit need to be?
A constant.
A constant, yeah. Some other constant. Let's call it, I don't know, a. All right. So here we now have the most generic representation of the integral of e to the negative x squared that we could get, right? The function that is the integral of that is y equals the integral from some constant a to x of e to the negative t squared dt plus some other constant. It's pretty generic. I got multiple different constants in there and I didn't integrate the function. I just put an integral sign in front of it. But the derivative of that, dy dx, is e to the negative x squared. True?
Yes.
How do I make this true? How do I make f of 7 equal 3? And maybe instead of writing a y here, we could write f of x is equal to that.
Could you just plug in the values for the certain variables, like plug in 7 for t and 3 for x and solve for c or something?
Well, the problem with doing that is I still wouldn't know what a is, for one. I need to get an actual value here for a, and the x has to stay as an x so that when I take the derivative of f of x, I get e to the negative x squared still. If I don't have an x up here, I don't get that. And so what we need is f of 7, which would be the integral from a to 7 of e to the negative t squared dt plus some constant to equal 3. Well, how can I make that true? You should be able to tell me a value for a and a value for c that will make that a true statement. How am I going to evaluate this? Sorry, just this. How am I going to evaluate this if I don't know what the integral of e to the negative t squared dt is? Seems like that's going to be impossible to evaluate, doesn't it?
Yeah.
Yeah, but it's not. There's one way that we could evaluate that and get a number for it. In fact, a very nice, easy number to deal with.
I don't know. What if you like took the derivative of both sides, or would that be like completely besides the point?
Derivatives here, no derivatives needed right now. A nice, easy way to evaluate this. Normally when we evaluate something, an integral, right, we can take the integral of it and then we evaluate at the upper limit, we evaluate at the lower limit, and we subtract it, right? Yeah.
So if you put a equals 7, would it just be 0 then, or?
Isn't that one of the rules that we previously had?
Yeah.
The integral from 7 to 7 of any function is 0. So we're going to just sort of cheat here and call a equal to 7. If a equals 7, then this whole piece is equal to 0. And what is your constant?
3.
3.
So we could then say that if f of x is the integral from 7 to x of e to the negative t squared dt plus 3, that ought to be the solution to this differential equation because it satisfies all the criteria. The derivative of f prime of x is e to the negative x squared, right? The derivative from a constant to x of this function is just this function in terms of x, that's e to the negative x squared. And the derivative of 3 is 0. We just get e to the negative x squared. Good or no?
But didn't you like make an assumption that like 7 was the constant? Aren't you like limiting yourself by doing that, or no?
We're limiting ourselves by the starting point of this integral, but couldn't I still then find f of 2 by plugging in 2 up here and integrate from 7 to 2, or find f of 1 and integrate from 7 to 1, or want to find f of 3 million, I could integrate from 7 to 3 million. All of those are integrals that can, I wouldn't say easily be approximated, but they can all just be approximated using any of our approximation methods, right? We're not limiting ourselves because we're not, we're not going to be finding explicit function. We're just going to be finding a numeric value that represents the area underneath this curve on some interval. And we should be able to do that for any real number.
But didn't you say that that function can't be integrated?
It can't be. That's true. It can't be. But what we can do with it is we can approximate that integral, right? And you can approximate the value of any integral using a left rectangular or a right rectangular or a midpoint rectangular or a trapezoidal rule. True?
Okay.
So we should be able to approximate the value to a very high degree of accuracy for f of 2, or f of 17, or f of a million, or f of negative pi, or whatever you want it to be, by just using a bunch of little subintervals, right? And our calculator will do it for us. Does that make sense to everybody or no?
Yeah.
All right, so what's f of 2? This is our integral. This is our solution. And what's f of 2? F of 2 ought to be the integral from 7 to 2 of e to the negative t squared dt plus 3. So you'll use your calculator, and you won't do t, you'll just do x when you do it. But just type that into your calculator. Integral 7 to 2 e to the negative x squared dx. Add 3 to it. And what do you get?
I got 2.996.
That was after adding 3 to it.
Yeah, before it's like negative 0.00 something.
Good. So if I were to, think about what that means is, well, the integral from 7 to 2, that's the opposite of the integral from 2 to 7, right? So that's basically saying that the value of the negative area under the curve, e to the negative x squared from 2 to 7 plus 3 is 2.996 is what that's saying. And so we should be able to use this idea for any function that we are unable to integrate to find the value of the function of any other x value we're interested in. So let's see if we can do this again. Hopefully we can try to do this again. You think we can or no?
We'll see. Probably not.
Probably not. All right. That's the right attitude to have. We want to find f of 2, and we're given f prime of x is x to the 4th sine x. So what should we do? We should write out that f of x should be equal to the integral from some value, some constant, to x t to the 4th sine t dt plus some other constant, because then the derivative of this is x to the 4th sine x and that satisfies this. So what does A need to be?
5 or 3.
A needs to be 3. And what does C need to be?
5.
5.
5, right? Because that way f of 3, which is supposed to be 5, should be the integral from 3 to 3 of t to the 4th sine t plus 5. And the integral from 3 to 3 of t to the 4th sine t is 0, plus the 5 gives you the 5. So our function, f of x, is equal to the integral from 3 to x, t to the 4th sine t, dt, plus 5. And so what does f of 2 equal? You'll just use your calculator and plug it in and tell me the approximation for that.
Why are we using the variable t instead of like x? Like, what's the point of switching them up?
The t we just call a dummy variable. It's just a variable that we use in there so that we don't get confused between x's up here and x's down here. It's just the common notation that's been used for hundreds of years now doing calculus.
All right.
There's no real reason for it. It's just what we do to have different looking variables there. Otherwise, it's a little like if I'm trying to evaluate, like if I'm trying to, hold on one second. Okay, sorry about that. So if I had an x here and I have x's in here, like I said, there's no real reason. It just sort of complicates it between a t and an x. I'm sorry, my kid was trying to get me to do stuff and I was a little distracted as I was trying to explain it, but I'm not sure what I even said. The t is a dummy variable. And so the dummy variable just represents any generic variable that we can put in here. It could be an x, it could be a y, it could be a z, it could be a theta, it doesn't matter. We just use something else to distinguish it from the x that's up there. It could be an x, but it doesn't have to be.
Cool.
Yeah.
I got negative 14.988.
Yeah, somebody just said that in the chat also, right? Negative 14.988.
Yeah.
Good. All right, we got one more of these, I think. I think you guys should do this one on your own. Ready? Ready, go. So hopefully you ended up with your function f of x was equal to the integral from 9 to x, since we're looking at f of 9 being 5, of 1 over ln t dt plus 5. And so that gives us, when we take the derivative, 1 over ln x, and when we plug in 9 for x, it gives us a 5. Is that what you all got for your function?
Yeah.
Okay.
Yep.
And with any luck, when you evaluated from 9 to 2, what did you get?
0.3239.
Sorry, say that again.
3.4.
0.324. Everybody good with that or no?
How do you know when you can't take the integral of something?
Well, that's a good question. There are just some functions that you can't. Like first one we dealt with, the e to the negative x squared, is a pretty common one. There's others like sine x over x that you can't do. And then I may just throw some in, like, I think 1 over ln x. I'd have to think about that. 1 over ln x, I believe, is another one that just can't be. But this one that we did before, x to the 4th sine x, can be integrated. You guys just don't have the tools for it. But basically, if they ask you to, on the AP test, on the calculator section, do something like this, you're going to know that it can't be integrated. Anything that's on the non-calculator section, you will be able to integrate unless it's a multiple choice and they just give you integrals as the answers, like, with an integral sign. But there's no like way to just know whether you can integrate something or not. So that's not really a very good answer for you. Sorry. there's just
It's
not.
okay. Thank you.
Yeah.
So could you use this method with things that like we can integrate then? Because it sounds like it's not exclusive to things that can't be integrated.
You could, but you're going to want to give me exact values on things and show your work on things that can be integrated. And I will personally make a distinction between when you should be able to do it and when you shouldn't be able and need to use a calculator. So, yeah, I think, let's see. What do we got here? Yeah, we got a couple more of these. What else we got? I think we'll stop there. We'll save these other velocity ones for tomorrow just to sort of get us going before we move into the next topics we're going to cover. So I think we're going to stop there.